Welcome to this video on linear algebra, focusing on partitioned, or block, matrices. This content is brought to you by Professor Manish. A partitioned matrix, or block matrix, is a matrix divided into submatrices called blocks. This is a notational and computational tool that changes only the matrix's organization, not the underlying matrix itself. As a definition, for a given matrix A, a partition divides it into blocks A_ij. Crucially, all blocks in the same row must have the same number of rows, and all blocks in the same column must have the same number of columns. Why partition matrices? It simplifies large matrix operations, makes structure explicit, and is essential for linear algebra proofs, numerical methods, machine learning, and optimization. It's also natural for distributed computation. Common types include the block row matrix, where the matrix A is horizontally partitioned into blocks, A_1 through A_k, and the block column matrix, where A is vertically partitioned into blocks. Other common types are the block diagonal matrix, which has non-zero blocks only on the main diagonal, and the standard 2x2 block matrix. Let's look at basic properties. For equality, two partitioned matrices are equal if and only if all corresponding blocks are equal. For addition, if matrices are partitioned conformably, blockwise addition works like scalar addition. Property 3 covers scalar multiplication. Multiplying a partitioned matrix A by a scalar lambda simply involves multiplying each block A_ij by lambda. Block matrix multiplication is very important. When multiplying two partitioned matrices A and B, the block sizes must be compatible, just like in ordinary matrix multiplication. For the transpose of a partitioned matrix, you swap the block positions and transpose each individual block, as shown in the example. The inverse of block matrices has a special case for a block diagonal matrix, where the inverse is found by inverting each diagonal block. General block inversion requires sure complements. For a block diagonal matrix, the determinant of A is simply the product of the determinants of the diagonal blocks dA_1 through dA_k. The rank property for block diagonal matrices states that the rank of A is the sum of the ranks of its diagonal blocks. In summary, partitioning is conceptual, not structural. Operations are valid blockwise if dimensions match, and block diagonal matrices are computationally efficient. Thank you for watching this video on partitioned block matrices.